Hello, students, and welcome back. We are going to begin studying related rates this week, and this is an application of the chain rule and implicit differentiation. These are classic problems for calculus, so I want you to be familiar with what related rates problems are and how to work with them. So the best way to try to describe it would actually be to go ahead and talk about one of the formulas that you'll probably encounter. So I'll just pick area of a circle. So if you're going to think about the area of a circle changing, let's say that the area of a circle is increasing. Well, related to that would be the radius of that circle. So as the area of the circle increases, the radius will be increasing as well. And so we'll be looking at the rate of change of the area and relating that to the rate of change of the radius. That's where we get this idea of related rates as one part of a formula changes, anything that's related to that is going to change as well. And we're looking at this with respect to time. So as you go through and do your differentiation to find the rate of change, you'll be doing that with respect to time. So that's going to mean doing the derivative with respect to time, d dt. And in fact, when you finish, you'll be solving for some unknown rate of change with respect to that time. So I'm going to go ahead and have us move to the back of your papers. We'll look at a classic ladder problem. And I'm going to go ahead and show you an animation of what's going on from this problem right after we read it. So we have an 8-foot ladder leaning against the wall. The top of the ladder is sliding down the wall at a rate of 2 feet per second. Hopefully you can imagine this, but maybe not have experienced it. How fast is the bottom of the ladder moving along the ground at a point in time when the bottom of the ladder is 4 feet from the wall? So I have an animation showing you here. So the ladder is starting up here on the wall, and it's sliding down the wall, and the bottom of the ladder then is getting further away from the wall. So we're going to look at knowing this rate of change. What is this rate of change going horizontally? Now, notice that this distance is getting smaller, so this rate of change is going to be a negative. This distance is getting longer, so this rate of change is going to be positive. And the ladder itself, which is in red, is not changing at all. So when we make our substitutions, we don't use a variable for the length of the ladder because it's not changing. But anything that is changing, like the length that it is from the floor to the top of the ladder, and then from the wall on the ground, how far it is from the wall, those things are changing. We'll use variables for those. So hopefully this reminds you to use Pythagorean theorem. All right, so let me get back to our page. So I'm going to go ahead and just quickly draw a sketch of the ladder here. We have 8 feet for the length of the ladder. I'm going to call this side X and this side Y. And I'm going to introduce to you how our variables will be given. Since we were told that the rate of change, that the ladder is sliding down the wall at a rate of 2 feet per second, and I called the part of the wall that the ladder was leaning against X, then dx dt, the rate of change of that length with respect to time, is going to be the 2 that we were given. But that distance is getting smaller. So it's actually -2, and this is in feet per second. And we were given another piece of information, and that is how fast is the bottom of the ladder moving along the ground when the bottom of the ladder is 4 feet from the wall. So I want to know when y equals 4 feet, what is dy dt? What is that rate of change of that distance? So this will be my unknown. Now, this y equals 4 is just for a moment in time, but that value of y is changing. So as I work to find my rates of change, I need to start with an equation where I have anything that's changing listed as a variable. So x squared plus y squared will equal, my ladder was 8 feet long, so 8 squared, 8 is not, the length of the ladder is not changing. I can go ahead and substitute in 8 squared and get 64. So this is going to be my equation that I'm going to use as a relationship between the x, the y, and the length of the ladder. And I'm going to do the derivative with respect to time. So notice that neither of those variables is a t, which means when I do the derivative, I have to do implicit differentiation. And anytime that I do a derivative of anything that is not a t, I'll have to have a d dt for that variable. So for example, x squared would be 2x dx dt. And then plus, I'll have a y squared. That's 2y dy dt. And then I can do the derivative of my constant, and that is 0. So now I can start to substitute in my given information. And I should only have one variable left, and that is what I was looking for. So I'm looking for dy dt. So as I scan my information, one thing I notice is that I don't have a value for x. But I can do some work, and you can do this at any point, but you may just end up doing it like I am when you discover that you need it. I know that I want to know what's going on when y is a 4. So I can substitute in just for this moment in time. For this moment in time, I can substitute in the 4 and find out what x is at that moment in time. So I'll do that. I'm going to subtract. So 4 squared is 16. I'm going to subtract that from both sides and get x squared equals 48. And then I can square root both sides of that. And I get an x value of the square root of 48, which will simplify to 4 square root 3. And again, that would be measured in feet. So now as I substitute in, and I'm going to substitute in with my units so that you can see what's happening with it. I have 2 times my x value, which is 4 square root 3, and that's in feet. My dx dt was given to me. That was -2, and that was in feet per second. So this is multiplied. And then I have plus 2, and then my given y value, and that was a 4. That's in feet. And I'm looking for dy dt. So dy dt is my variable. And that equals 0. So I'll be calculating 2 times -2 times 4 square root 3, and that would be negative 16 square root 3 feet squared per second. And I can add that to the other side of the equal sign. So I'm going to multiply this together and then add it to the other side of the equal sign. So I'm going to do that work up here. I'm just having trouble fitting this all in. So that leaves me with this part of the equation. This is 8 feet dy dt equals, and then I've got, since I'm moving to the other side, 16 square root 3 feet squared per second. And then I can solve for dy dt by dividing by 8, and that's 8 feet. And so 16 divided by 8 would give me 2 square root 3. And then feet squared per second, when you divide by feet, is just going to leave you with feet per second. And I put those labels in there because I do want you to have labels. For some of you, especially those that have been through physics, you've seen putting labels through the equation before. I will not count off if you don't put them as you're working the equation, but I do want you to have your units in the final answer. So if it helps you to have them throughout the equation to see how they will cancel out or multiply together, then that would be an example of how to do so. So the rate of change of the distance that the ladder is going, the base of the ladder going away from the wall, ends up being 2 square root 3 feet per second. And that would be a rate related to the rate that it's sliding down the wall. Okay, so there's your first one. And we'll move on. I'm going to clear the ink and look at your second one. So the second problem is a point moving along the graph of y equals the tangent of x. And it gives you that dx dt is 2 centimeters per second. It wants you to find dy dt. And this is a sneaky little thing that some of these problems have. It'll say when x is negative pi over 3, and then surprise, part B, when x is negative pi over 4. Once you have part A completed, part B is just a matter of resubstituting in. So really not a lot more work. All right, so I wanted you to visualize this. I have a graph of y equals the tangent of x pulled up here. Now this one is not animated, but this is your tangent graph. And so when x is negative pi over 3, and that's right around, I think it was right in here, we're trying to find the rate of change of your y value. So I'm going to get it back to my problem. And so we don't really have a diagram that we need to draw for this one. We can just start working on the derivative. So we'll do the derivative with respect to time of y equals the tangent of x. So derivative with respect to time of your equation. And so that would make us have dy dt equals, and then the derivative of tangent, which is secant squared. We keep our angle x, but because our angle is an x and we're doing the derivative with respect to time, we'll have to multiply that by dx dt. All right, so if we look at our given information, we're told that dx dt is 2 centimeters per second. we have to find dy dt, and we know an x value to start with, part A, is negative pi over 3. So dy dt will equal, and secant, I'm going to go ahead and change to 1 over cosine, and I'm going to substitute in my negative pi over 3. This is the moment in time that we're considering, and it is squared. Our dx dt is 2 centimeters per second. And so this is being multiplied. All right, so the cosine of negative pi over 3, that would be in the fourth quadrant, and your cosine value is 1/2. So we'll be making that substitution. Dy dt would equal 1 over 1/2. And then remember that this is squared. And we're multiplying this by 2 centimeters per second. And so if you will square and also multiply by the reciprocal, you'll end up getting 4 times 2, which is 8 centimeters per second. And so for part A, 8 centimeters per second is when x equals negative pi over 3. Now, make sure that on something like that, you do identify. So this is part A, when x is negative pi over 3. I can change colors, and so it's a little bit easier for me to identify it. Make sure you identify it in your work. Part B is when x is negative pi over 4. So I'm going to go ahead and put that here. If x changes to negative pi over 4, we don't need to do the derivative again. We just need to change our substitution. So when x is negative pi over 4, then our dy dt would equal 1 over the cosine of negative pi over 4. And that is squared, and then also times 2 centimeters per second. The cosine of pi over 4 is square root 2 over 2. So it's 1 over the square root of 2 over 2. And then that gets squared. And so your final answer on this, well, let me go ahead and show. So 1 over the square root of 2 over 2. This gets squared. You're taking that times your 2. Again, that's centimeters per second. And your final answer for dy dt, when in part B, I'm going to move up here. Dy dt will equal, and that turns out to be 4 centimeters per second. So 4 centimeters per second for that one. And you can do the arithmetic on that to get the answer. So these problems are not as difficult to set up usually. And your differentiation, I think you'll find, is much easier. All right, so there's one using a trig function. I'm going to show you just one more to let you see just another formula that's being used, and to let you know that except for the Pythagorean theorem, I will give you formulas. So this next one is about a sphere. I would like for you to know what the volume of a sphere is, but that is not something that I will require. So if you need a formula like that, I can give it to you. So let's look at problem 3. And for problem 3, it talks about the radius of a sphere increasing at a rate of 2 inches per minute. So the rate of change of the volume when the radius is 6, and then when the radius is 24 inches is what we're considering here. So on a sphere, the volume is 4/3 pi r cubed. And I wanted to include this because a lot of times students will mistakenly treat pi as a variable, but pi is a constant. It's a coefficient in this case. So just be aware of that as you're working with the derivative. All right, so we're starting with this. You have a sphere. You can imagine that like a balloon or a beach ball being blown up. And we have that increasing radius. So now we're wanting to find the rate of change of the volume. All right, so we'll do the derivative with respect to time. And so the rate of change of the volume with respect to time will be dv dt. As you do this, we really only have r to the third as our variable. So we can do the power rule. So bringing the 3 times the 4/3 pi, the 3's would cancel, and we would have 4 pi r squared. And then since the r is not a t, we'll have to multiply by dr dt. So this is looking for the rate of change of the volume at the moment in time for part A when the radius is a 6. So we're looking for dv dt. And the radius given to us first is 6. And it says the radius of a sphere is increasing. So it's getting bigger at a rate of 2 inches per minute. I'm going to go ahead and put those units on that 6. So the 6 would be inches, and this gets squared. And then dr dt is 2 inches per minute. So we can see the units on the volume. So dv dt, and we'll leave our answers in terms of pi, is going to be 4 pi. And really, I know you could do this on a calculator all at once. I'm just trying to help you out here with the units a little bit. So 6 inches squared would be 36 inches squared, and then times 2 inches per minute. If you multiply those together and leave it in terms of pi, then dv dt is going to turn out to be 288 pi. And then notice that you have inches squared times inches. That's going to be cubic inches or inches cubed per minute. And again, this is dv dt, the rate of change of the volume with respect to time. That's part A when the radius is 6 inches, so fairly small. So if you imagine a beach ball being blown up and now the radius is 24 inches, let's look at part B. So in part B, when the radius is 24 inches, now we can substitute in. So dv dt would equal 4 pi times 24 inches squared, and then times 2 inches per minute. And so your number gets much bigger there. And I'm just going to go ahead and multiply that out for you. So if you take 4 times 24 squared times 2, you'll end up with 4,608. Don't forget that you have pi, 4,608 pi. And again, it would be inches cubed per minute. All right, so you've seen some couple of classic problems, one with the ladder and another with a sphere. You also saw one with trig. So you're going to be doing some related rates problems in this first lesson where you'll be making those substitutions. Remember, if something changes, you substitute for it. If something remains constant, you can leave that amount in and then do your derivative. So good luck on your homework as you begin this lesson.